The gradient is a fundamental concept in multivariable calculus and machine learning. It's a vector that points in the direction of steepest ascent of a function. Mathematically, the gradient of a function f is a vector containing all its partial derivatives. For a function of two variables, the gradient is defined as follows. For example, consider the function f x, y equals x squared plus y squared. Its partial derivatives are 2x with respect to x and 2y with respect to y. At the point 1, 2, the gradient would be the vector 2, 4, pointing in the direction where the function increases most rapidly. Let's visualize the gradient on a contour plot of the function f x, y equals x squared plus y squared. These lines represent points with the same value of the function. The gradient points perpendicular to these lines. Notice how the gradient vectors always point outward from the center, perpendicular to the circular contour lines, and get longer as we move farther from the origin where the slope is steeper. This is a heat map showing the height of the function. Brighter areas are higher. We again add the gradient vectors, showing the direction of steepest ascent. Imagine you're hiking on a mountain. The gradient tells you which direction is the steepest uphill path at your current location. If you want to climb fastest, follow the gradient direction. To descend fastest, go opposite the gradient. In machine learning, gradients are crucial for training models. The gradient of the loss function tells us how to adjust parameters to minimize error. During backpropagation, we calculate gradients for each parameter, then move opposite to the gradient to reduce loss. This is called gradient descent. The gradient's direction tells us which way increases the loss, so we move in the opposite direction to minimize it. The chain rule is one of the most important rules in calculus. Especially for machine learning, it allows us to compute derivatives of composite functions. Mathematically, the chain rule states that the derivative of a composite function is the product of the derivatives of its components. For two functions f and g, in Leibniz notation, if y depends on u which depends on x, then dy dx equals dy du times du dx. For multiple compositions, we multiply all the derivatives along the chain. This becomes crucial in neural networks with many layers. Let's work through a simple example. Consider the function y equals sine of x squared. We can break this into two functions, u equals x squared, and y equals sine of u. Now we compute derivatives, du dx is 2x, and dy du is cosine u. Applying the chain rule, dy dx equals dy du times du dx, which gives us cosine x squared times 2x. In neural networks, the chain rule enables backpropagation, which is how networks learn from data. Each layer's output becomes the next layer's input. To compute gradients for the early layers, we multiply derivatives backward through the chain. The chain rule allows us to efficiently compute how each weight affects the final loss, even in very deep networks with millions of parameters. Let's visualize the chain rule with a computational graph. This shows how derivatives propagate through operations. Forward pass computes values, x flows to u equals x squared, then to y equals sin u. Backward pass computes derivatives. dy do is cosine u. Do dx is 2x. And by the chain rule, dy dx is cosine u times 2x. Gradient descent is the workhorse optimization algorithm behind most machine learning models. It uses gradients to iteratively minimize a loss function. The gradient descent algorithm updates parameters by moving in the direction opposite to the gradient of the loss function. Here, theta represents the parameters, alpha is the learning rate, and the gradient term points in the direction of steepest ascent. By subtracting the gradient, we move in the direction of steepest descent, gradually minimizing the loss function. Let's visualize gradient descent on a simple quadratic loss function. The algorithm takes steps proportional to the gradient at each point. Starting at a random point, we compute the gradient, which gives us the direction and magnitude of the steepest ascent. We then take a step opposite to the gradient direction. The size of this step is controlled by the learning rate alpha. This process repeats until convergence. Notice how steps get smaller as we approach the minimum where the gradient is 0. The learning rate alpha is a crucial hyperparameter. Too small, and learning is slow. Too large, and we may overshoot the minimum. With a small learning rate, convergence is slow but stable. The algorithm takes many small steps toward the minimum. With a moderate learning rate, we reach the minimum efficiently in just a few steps. With too large a learning rate, the algorithm may oscillate or even diverge, never reaching the minimum. There are several important variants of gradient descent used in machine learning. These variants offer different trade-offs between computational efficiency and convergence stability. Gradient descent powers nearly all modern machine learning, from linear regression to deep neural networks with millions of parameters. Batch gradient descent is the most straightforward version of gradient descent. It uses the entire training dataset to compute the gradient at each step. Let's look at a simple linear regression problem with a small dataset. Here we have house sizes and their corresponding prices. In batch gradient descent, we'll use all these points together to calculate the gradient at each step. The update rule for batch gradient descent computes the average gradient over all training examples. Before updating the parameters, here, m is the number of training examples, alpha is the learning rate, and the summation calculates the average gradient across all examples. Let's visualize how batch gradient descent works on a simple quadratic loss surface. Batch GD computes the exact gradient using all data points, resulting in smooth, direct paths toward the minimum. Notice how each step is straight toward the minimum, without oscillations, because we are using the true average gradient. Let's visualize how batch gradient descent works on our linear regression problem. We start with random parameters. Here's our initial hypothesis line. Now we'll perform batch gradient descent. First, we calculate the gradient using all data points. The average of these gradients determines our parameter update. After the update, our line fits better. We repeat this process until convergence, always using all data points for each gradient calculation. Batch gradient descent has both advantages and disadvantages. Batch GD is best suited for small to medium datasets where computing the full gradient is feasible. Stochastic gradient descent, or SGD, takes the opposite approach of batch GD by using just one random training example for each gradient. Update. Let's use the same house price dataset we saw earlier, but now we'll process it differently for SGD. In SGD, we'll process these points one at a time in random order, unlike batch GD which uses all points together. The SGD update rule uses the gradient from just one randomly selected training example. Here, I is a randomly selected index from the training set. This makes each update much faster but much noisier than batch GD. In practice, we shuffle the dataset and iterate through examples one by one, which is equivalent to random sampling. Let's visualize SGD on the same quadratic loss surface. Notice how the path is much noisier. Each step is based on a noisy estimate of the true gradient, causing the path to zigzag toward the minimum. This noise can actually help escape local minima and find better solutions, which is why SGD often outperforms batch GD in practice. Let's see SGD in action on our linear regression problem. We start with random parameters, just like before. Now using point 3, size 2.0, price 500. Now using point 6, size 3.5, price 700. Now using point 2, size 1.5, price 350. Now using point 4, size 2.5, price 550. Now using point 1, size 1.0, price 300. Now using point 5, size 3.0, price 600. Notice how each update dramatically changes the line based on just one point. The final result is good, but the path was much noisier than batch GD. Stochastic gradient descent has unique advantages and disadvantages. SGD is ideal for large datasets and non-convex problems where batch GD would be too slow or get stuck. Mini-batch gradient descent strikes a balance between batch GD and SGD by using small random subsets of data for each update. Let's use a house price dataset again, but now we'll process it in small batches. We'll divide these 12 points into 4 mini batches of 3 points each for our updates. The mini batch GD update rule computes the average gradient over a small random subset of examples. Here, B is a randomly selected mini batch of size B, typically between 32 and 512 examples in deep learning. This combines the stability of batch GDs averaging with the efficiency and noise benefits of SGD. Let's visualize mini batch GD's path. It's smoother than SGD but still has some noise. The path is less erratic than SGD but more flexible than batch GD, often finding better solutions. This balance makes mini batch GD the default choice for training most neural networks. Let's see mini batch GD in action on our linear regression problem. We start with random parameters. Processing batch 1 with points 1, 2, 3. Processing batch 2 with points 7, 8, 9. Processing batch 3 with points 4, 5, 6. Processing batch 4 with points 10, 11, 12. Notice how each update is based on several points, making progress smoother than SGD but faster than batch GD. Mini batch gradient descent combines the best aspects of both extremes. Mini batch GD is the gold standard for most deep learning applications today. Momentum is a technique that accelerates gradient descent by accumulating a velocity vector in a direction of persistent reduction. Let's consider a linear regression problem with our house price dataset to demonstrate momentum. We'll use mini batches of 3 points each, and compare standard SGD with momentum-enhanced updates. Momentum introduces a velocity term that accumulates past gradients with exponential decay. Here, beta is the momentum coefficient, typically 0.9, controlling how much past gradients affect the current update. Let's compare standard SGD with momentum on a loss surface with ravines. Standard SGD oscillates in the steep ravine, making slow progress along the shallow dimension. Momentum builds up velocity along the shallow dimension while cancelling oscillations in the steep dimension. This acceleration along consistent directions and dampening of oscillations makes momentum much faster in practice. Let's see momentum in action during training with our mini batches. We start with random parameters and zero velocity. First, let's see standard mini batch GD without momentum. Now let's see the same training with momentum added. Notice how momentum helps maintain consistent direction in parameter space, leading to faster convergence. Momentum provides significant benefits but also has some considerations. Momentum is almost always beneficial and is used in nearly all modern optimization variants. I hope you found this video helpful. If you enjoyed it, please give it a thumbs up. Subscribe to the channel. Leave a comment, and share it with your friends. Your support means a lot. See you in the next video.